Hello, my name is Rob McLean, and I am an analytical laboratory director. And I'm going to tell you a little bit about the ICP instrument that we're going to use to measure the lead in the samples that you have generated in your Chem 329 laboratory. This is the instrument that we're using to measure the lead in your samples. There's two major parts to the instrument. If you look at this picture, you can see on the left side there's the plasma part of the instrument. That's where the ICP comes from, inductively coupled plasma. On the right side of the experiment or the instrument is the spectrometer. That's where the OES comes from, optical emission spectroscopy. We're effectively going to burn your sample in the plasma and look at the emission with the spectrometer. The ICP instrument is essentially just a flame test. Okay? You're all familiar with the idea of fireworks. In fireworks, we put metal compounds, metal salts typically, with the explosives, and when the firework explodes, the high temperature firework, the elements that are in the firework from the metal salts, they will emit characteristic colors based on the identity of the metal inside. So, like for example, lithium glows at like a pretty reddish color. Potassium gives you a purplish color. Magnesium actually gives you a very nice bright white color. And boron glows a nice green color. Okay? Well, in the ICP instrument, we're going to take your liquid sample. There's a pumping system and a nebulizer to make a spray out of that liquid sample. And that sample is going to be introduced into the high temperature plasma. In that plasma, your sample is completely obliterated. There any kind of molecules, any compounds, any complexation, any solvation, all of the stuff just completely consumed in the plasma environment. The elements that are in your sample, they get consumed and atomized to create free atoms or free ions of all of the elements that are in your sample. And then what we do is with the monochromator, we just look at emission of light from plasma. With the monochromator and a detector, we can detect specific wavelengths. So remember, the wavelengths of emission are going to be determined by the electronic states available for the elements, and the emission of lead is very different than the emission of, say, magnesium, the emission of sulfur, or any other metals or compounds or any other elements that might be in your sample. When you bring your samples in these small 15 milliliter centrifuge tubes. It only takes about 3 to 5 milliliters of solution to make the measurement, but give yourself a little bit of leeway, so maybe 5 to 10 milliliters of your solution in the centrifuge tube. Make sure the centrifuge tube is clearly labeled. It just makes data record keeping a little bit easier. And then we'll put these centrifuge tubes in the auto sampler of the instrument. We'll load up your sample, and maybe some samples from other students, other groups, into the auto sampler. And then we program the instrument to introduce each sample and look at the emission of lead from each sample. The output of the instrument is just this very narrow range of wavelengths where we look at the peak. In this case, the peak of lead is at 220 nanometers. And the height of that peak, or the area under the peak, is proportional to the amount of lead in your sample. Now, to do an unknown, we do have to first generate a standard curve by running a set of lead samples of known concentrations. That way, when you look at the emission of your unknown, you can compare it to your standard curve and determine the concentration of the lead in your unknown.